Hello friends, in continuation with the last lecture, today we are going to talk about the junction breakdown. Means what is the effect when we are trying to apply the sufficiently high field to the PN junction, right? Means how the junction gets break down as and the conducts a very large amount of the current, right? So when the PN junction generally conducts very heavily, generally when it is as we know that it is connected in the reverse bias potential is applied across it, right? So the actually the PN junction breakdown occurs only in the reverse bias region because the high voltage can be applied and that results into the breakdown of the junction. Now there are basically three types of the mechanisms, okay, which are the thermal instability, tunneling phenomena, and the avalanche multiplication. In these three ways the junction breakdowns can be happen only in the reverse bias cases, okay. Now let's talk about the briefly in the first two uh, junction breakdowns, and then maybe in detail we'll talk about the avalanche multiplication in the next lecture, right? So the first one, the thermal instability, right? So thermal instability means actually it is related to the what we call it is a temperature, right? So this is due to the temperature effect or the thermal effects, okay. So this is instability is responsible for the this type of the instability is responsible for the high dielectric strength in most of the insulators at particularly room temperature, because room temperature is also the sufficient energy to have the junction breakdown, and also the major effect in the semiconductors with actually when we are trying to dope that particular semiconductor heavily, or else we can have the relatively small band gaps, right? So now what happens that the due to the heat, that is kT amount of the energy, or 3 by 2 kT if it is three dimensional world. So because of the heat dissipation and caused by the reverse current at high reverse voltage, means when we are trying to apply the high reverse voltage, means the, okay, if it is P and N junctions, then here we can have the negative potentially and positive potentially given to the P junction, P type of the region. So this is how when we are trying to apply the very high voltage across it, so obviously the high amount of the reverse current also gets flows through it, because the this deflection region goes on increasing. So for that one to have the junction breakdown, we need, when this depletion layer goes on increasing, its width goes on increasing. When this depletion width touches to the end of the either of the regions, then there it starts conducting very heavily, right? So now the junction temperature, when this high voltage is applied, the junction temperature gets increases. So this temperature increase in turn increases the reverse current in comparison with its value at low voltages. So now actually this is something like the positive feedback for it, because the thermal instability that thermal motion increases the current in the opposite direction, means in the reverse direction. So this is actually considered as a positive feedback, which is responsible for the breakdown of the PN junction. Now the temperature effect on the reverse current voltage characteristic can be seen from this figure as well, right? So in this figure what we can have, the reverse current densities are represented by this family, reverse current densities. So reverse current density is represented with the JR in ampere per centimeter square. It is on the vertical axis. On the other hand, the horizontal and that is horizontal lines which are parallel to the reverse voltages applied to it, right? Now so the each line actually this each line represents the at the constant current. So the J0 is some at some constant temperature we are trying to, and trying to study this characteristics. So J0 at some one particular constant temperature. So now this lines, actually this current follows the curve something like I is proportional to the t raised to 3 plus gamma by 2 exponential of minus Eg by kt. So such a kind of the curve it follows. Okay, okay. So now yes, you might have a little bit idea about it. Okay, so now this heat dissipation parabolas, which are actually, so we can have this current. So this kind of the curvature we are just talking about. So this type of the hyperbolas which are proportional to the power. So this type of the parabolas are proportional to the power. Power is nothing but the current into the voltage. So we know that the this is a current and this is voltage. So if we take the product of that, means the area under that curve gives us the power. So and the sloped lines or straight line in the log plot gives us this hyperbolas, right? So if we can have this slope lines, so that will give us the hyperbolas corresponding to it. So these line also have to satisfy the curves of the constant junction temperature. So constant junction temperatures we can have here. Okay, so the reverse current voltage characteristics can be obtained by intersection points of these two set of the curves. So these two sets of the curves, so these are the intersection points where we can obtain this characteristics curve for the corresponding to. So this is actually the characteristic curve for corresponding to it. Why? Because of the heat dissipation at the high reverse voltage, the characteristic show a negative differential resistance. Negative differential resistance, because here we can have the current is also increasing and the voltage also increasing, current increasing and the voltage increasing. So that is a negative differential resistance. So in this condition, the diode will be destroyed unless the some special measure such as the large series limiting resistor is used. So this effect actually called as the thermal instability or the thermal runaway. Okay, so the voltage corresponding to this point, okay, voltage corresponding to that intersection point is called as the over voltage and represented with the phi u. Okay, so it is represented with the phi u. So the for any kind of the p-n junctions with relatively large saturation currents, okay, relatively large saturation currents, that is in kind of the germanium, the thermal instability is very important, because the what we can say, the thermal instability is very important in a small band gap semiconductors, but for the very low temperatures it becomes less important compared with the other mechanism. As we can see over there, that breakdown voltages are going to get decreased, or turn on voltage goes on decreasing when we are having the temperature is changed from the low temperature to the high temperature. Okay, and even this curves also you can see over here, the current density also get decreases as the temperature goes on increasing one. Okay, so this is related to the thermal instability. Now the other effect is nothing but the tunneling phenomena. As we are quite aware of the tunneling, this is something like the passing through it. Okay, passing through it. So here we consider the tunneling effect. Okay, now when the junction is under the large reverse bias, again this is also the under the reverse bias condition. Okay, reverse bias or reverse bias voltage is applied, and that is also the large we are applying over here. Okay, so now it is actually well known that the carriers can miss when we are trying to apply the large voltage, reverse bias voltage, then the carriers can tunnel from this region to the this region, this region to the this region. Okay, so the it can tunnel through the potential barrier if the barrier is sufficiently, so this need to be reduced, or it should be the very less amount of the or sufficiently thin barrier should be there, and this is because of the induced field. Okay, large induced field. Okay, and this is field effect. Okay, tunneling phenomenon is almost related to the, most of the time it is related to the field effect, because the potential is applied across some distance. So the potential upon distance can give us the electric field. So in this particular case, the barrier has a triangular shape. Okay, so this is a kind of the triangular section shape over here, and here also it is a triangular one. So this is p side and this is on the sorry, this is n side, this is p side, we can consider over here. So now the barrier has a triangular shape with a maximum height given by the this energy band gap. So the energy band gap, this maximum height of this triangle can be extended up to here. So this maximum height can be given by this depends upon the energy band gap. Okay. Now when we are trying to consider the tunneling current, okay, so its derivation I am just trying to write down, directly taking its value, that is tunneling current density is given by some particular relation, that is 2 m star q3 up electric field into Pr, it is reverse potential, then 4 pi square h cross square under root Eg into exponential of minus 4 root 2 m star Eg raised to 3 by 2 upon 2 q electric field h cross. So this is I am writing the direct relation or direct result, okay, and maybe sometimes later we will try to look into this particular result as well. So here the field is not constant, okay, field is not constant because that is varying. We are trying to vary the potential applied to it. So obviously the field gets changed. So E is some average field inside the junction, okay. This E I am just talking about this average electric field. So now when this field is goes very high, that is almost few thousands of the volt per centimeter, okay, few thousands, I am talking about its field around 10 raised to 6 volt per centimeter, this much amount of the field is applied, okay, in case of the some silicon or the other related semiconductors, the significant current starts to flow by means of the band to band tunneling process, band to band tunneling processes when the such a high field is applied. Okay. So no, so to obtain such a high field, the junction must have the relatively high impurity concentration. So to get such a amount of the high field, what we must have, it should be that junction has to be have the very high impurities to be doped inside it on the either side, on the whether it is a p side or the it is a n side, on the both sides it should be highly doped. Okay. So the now this mechanism of the breaking down mechanism actually happens okay, when now there that's this breakdown voltage, if it is less than or less than 4 eg by q voltage, 4 eg by q, then it is because of the tunneling phenomena. Okay. If it is that breaking down voltage is greater than 4 eg by q, if we need to have the this voltage greater than this one, then we will having the avalanche mechanism. Okay. The breaking down is happening because of the avalanche multiplication. Okay. On the other hand, if this breaking down voltage is in between these two, then the obviously the both the phenomena, okay, both the phenomena are trying to break down the or contributing to the breaking down of the PN junction, that is the tunneling as well as the avalanche multiplication. Okay. So now since the energy band gaps in case of the silicon and the gallium arsenide decrease with the increasing temperature, okay, that is a negative temperature coefficient. So increasing energy band gap in the silicon or the gallium arsenide decrease with increasing the temperature. So the breakdown voltage in this semiconductor due to the tunneling effect and has a negative temperature coefficient, that is what I said. Okay. That is breakdown voltage decreases with increasing temperature. This is because of the given breakdown current that is can be reached at smaller reverse voltages at the high temperature. Okay. On the other hand, we can have the other kind of the material as well, that is the temperature effect is generally used to distinguish the tunneling mechanism from the avalanche mechanism, which has the positive temperature coefficient, that is breakdown voltage increases with the increasing temperature. Okay. So this is what the we have talked about the tunneling phenomena. So So on we'll talk on the next topic, that is avalanche mechanism, maybe on next lecture.